And welcome to today's closing keynote at 6GSymposium. I'm Alex Lawrence, the managing editor of 6G World, which is a site for news, comment, events, podcasts, and more, exploring what the world of 6G might look like and how we get there successfully from here. Now, I'd encourage people who don't already subscribe to our newsletters every 2 weeks to try it, as we'll be bringing out some new capabilities and updates this year, which will hopefully be useful for you. But that's enough of that pitch. If you've seen any of the day's activities, you'll know that the path to 6G, whatever 6G ends up looking like, will be built to a significant amount on the foundations of 5G. There's just no commercial appetite for reinventing the wheel once again. And now we're fortunate this afternoon to explore two aspects of this in detail with our event sponsors Cohere Technologies and Roden Schwartz, as we explore the role of cloud and AI. A variety of speakers today have already touched briefly on the subjects, and I don't want to steal our speakers' thunder by giving too much away on the topics. So let me just set out the order of play and then hand over to our first speaker. This afternoon, we're being joined by Andreas Rösler, 6G Technology Manager at Roden Schwartz, and we also have Cohere Technology CEO Ray Dolan calling in from Davos. Now, I'll give Ray time to speak first and then hand over to Andreas. We're going to have plenty of food for thought across the technology and business considerations, and I suspect we'll be pressed for time. So please do feel free to leave questions or comments in the Q&A box. I can't promise that we'll get to them in the session, but I am pretty confident that we can follow up offline afterwards, even if we can't respond here. So with that housekeeping done, Ray, I'd like to hand over to you.
Well, thank you very much, Alex, and greetings to all of the folks around the world that you've called together in this 6G World conference. And congratulations to you as well, Alex, for pulling this off in a semi-post-COVID world. Hopefully we'll fully get there, and as we talked about a little bit before, hopefully we'll all be together personally in 6 months in our personal form. For all those that are out there, my name is Ray Dolan, and I am the CEO of Cohere, and I've been in the industry since 1986. And I offer that as background because my view of 6G is kind of framed in the context of my own personal experience, from analog cellular in 1986 with Pactel Cellular in Los Angeles, to being part of the transition to 2G digital in New York City, to harmonizing the voice around CDMA all around the world, and then 4G being really mostly about mobile internet. I happen to be a co-founder and CEO of a company called Flareon Technologies. When what I experienced there was we were proposing that the internet would be mobilized in its current form. For those that were in the industry then, you know that we were also exploring this notion where there'd be a mobile internet, and there was this protocol called WAP that was going to create two different worlds, a wireless world and a wired world. And that looks silly now in retrospect, but honestly, there was a lot of smart money on that WAP protocol and operating systems around that, like Symbian and other Palm OS. So that kind of informs my thought as to how we're going to move to cloud, which I'll talk about in just a few seconds when we move to that single slide that I'll use. Of course, we're now involved in 5G. I'm involved in the Cohere context of 5G because 5G is really all about moving to MU-MIMO, moving into the enterprise, and really going to broader, fatter pipes, and also going up the frequency band into millimeter wave. But what is 6G going to be about? And as we give this thought, fundamentally, 6G is about moving to a cloud architecture. And the reason I shared the context of 4G being all about the mobile internet is there's still a lot of confusion in the wireless industry as to whether or not we're going to really fully embrace cloud architectures. And there's a pretty strong resistance to it because there's a debate about whether or not you can, in fact, move the intelligence that lives in a base station to a data center and open up the architecture of the wireless network to a cloud architecture that hosts multiple waveforms. And that is, in fact, Cohere's thesis. It is our view of where the architecture is going. It's where we're investing, at least as one company. Time will tell whether we're right or not, but I'd like to share with you at least our progress along the way, because all of the signals are looking very good for that architecture to work. First of all, we believe it will host multiple waveforms, 4G, 5G, 6G. So when people have this discussion, will 6G be a different waveform? We actually believe that 6G will be multiple waveforms that all run on a common cloud platform, and that those waveforms should in fact be optimized for the applications that are working underneath it. In wireless up until now, we have argued and then coalesced around a common architecture, and then we've compromised some of the unique attributes that would be required for certain applications. But in the future, we see there'll be a waveform that's optimized for autonomous vehicles, a waveform that'll be optimized for IoT, thin applications that have hyper reliability, hyper low latency requirements. There'll be other waveforms that might be optimized for broadband access and multimedia streams. There might be a new waveform created for augmented reality and industrial automation, what have you. Or at least modified waveforms that have multiple common architectures, but then they have different degrees of freedom from a design parameter point of view. And they'll all be hosted naturally on a common cloud platform. Now, contrast that to where people are trying to do 4G and 5G in the same box. Most people in the industry call that DSS. And there's a significant struggle that the industry is going through right now. First of all, just making it work. And then second of all, seeing performance of both the 4G and 5G network degraded in order for them to achieve kind of the lowest common denominator. We're talking about something completely different. We're talking about a cloud platform that allows the intelligence of the base station, the scheduler, and the channel sensing, detection, estimation, and prediction mechanisms, all of that to move in software to the data center. Now, there are a number of folks that don't believe that's possible. We have actually done it. It is, in fact, not possible in today's time frequency domain, but it is possible if you invert time frequency into delay Doppler, and that's really where Cohere has been focused for the last decade. All right, and so that's how we see 6G coming together, is adopting a cloud architecture. So again, remembering back to the 3G, 4G debate, the 3G multimedia architecture of wideband CDMA tried to capture the marketing momentum of the internet by asking the internet to conform to it. The internet was bigger than wireless, and as a result, we now have a wireless protocol that in fact allows TCP/IP and all of the internet protocols to move seamlessly. We take that for granted today. I'm dialing in right now on an iPad. It happens to be over a Wi-Fi network in a hotel, but it could easily be over a 4G LTE network. It's the exact same experience that everyone else is attending through, regardless of whether you're on a wire or a wireless network. We're actually over the internet. Okay, so we have a common access modality. We've conformed as an industry. The cloud is as big or bigger than the internet, and wireless needs to conform to cloud. Okay, as opposed to having a wireless cloud that's different than cloud. What we need to do is take the intelligence of the base station and move it and co-locate it in a data center so that applications can enforce their requirements across wireless, just like they can enforce the requirements across any other modality on a wire. And as challenging as that may seem, it is entirely possible, and that's where we believe 6G is going. So we see a 6G world where the base station left behind is radically simplified. It will still have multiple waveforms, or what people call modulation schemes. It'll have a significant amount of compute, and it will probably have some intelligence and scheduling in it. But most of that intelligence and scheduling will move to the data center, and a number of very positive benefits will accrue from that. One, it'll be much easier to do network slicing, when in fact, the scheduling and intelligence is sitting right next to the user plane function, which is what knows what the user needs. Okay. And then two, that intelligence will see across the city of Los Angeles or across the city of Zurich or across the city of London, as opposed to managing interference just on a base station by base station basis. Because most people in wireless industry know that the interference at the system level is about 50% within a base station and about 50% between base stations. And there's no way to control between base stations unless we move the brain back to where it sees across the system. So those are the architectural issues that I think 6G will address. I think we'll get out of the 10-year cycle of modulation scheme development where we argue for 4 or 5 years, settle on an idea, implement it over a 4 or 5 year period, and then do the same thing all over again 10 years later, right? If you think about the pace of the application universe changing, and you look at the software pace of the cloud being almost every other day, or certainly no more than every week, these massive cloud networks are upgrading themselves on the fly in virtual containers. It's time for the wireless world to move beyond the 10-year cycle of Gs, or even the 1-year cycle of 5.2 or 5.3G into a much faster, more agile software environment. So Alex, those are the thoughts that I wanted to share with your audience today. I hope it stimulated some thinking as to what's possible in the industry as we embrace the cloud as an architecture, challenge ourselves to move the intelligence to the data center and bring the data center into the architecture, just like a central office was brought into the architecture through what used to be called an MTSO. I'll open it up either for your comments in response to me, Alex, or if you'd like, we can move over to Andreas at this point.
Thanks, Ray. Yeah, I do have one question, and that's, I guess, to do with the structure of the industry. I mean, you talk about moving away from this 10-year cycle of between generations, and at the same time, we've seen a number of times today organizations like the standards bodies and so on, and indeed governments looking at almost exactly this kind of a cycle of research, standardization, commercialization. Do you think that, well, I mean, there's clearly a conflict there, but I'm just wondering how that gets resolved.
So let me make sure I understand your question. So governments and universities are proposing extended cycles of research prior to the decisions we would make with regard to next generation?
Yes, that's right. There looks to be a sort of waiting until 2030, let's say, for a 6G rollout.
Well, there's probably some like that. I have not experienced as much of that as you might have, Alex. I'm seeing, particularly in the United States, I see a tremendous urgency to drive open networks faster than people are driving them today in 5G. I also see a desire to introduce cloud architecture to open the supply chain to a much broader range of companies. And I think that's an architecture for 6G. Where I do share your experiences in areas where people say, let's not issue more spectrum for 6G until they've consumed 5G. So maybe, because it used to be the Gs were mapped to spectrum options and allocations. I don't know that that's necessarily needs to happen here. So I don't see the tension between research, government, focus versus moving faster.
Okay, thanks very much, Ray. We do have another question in here from an anonymous attendee, so it would be difficult to follow up offline, saying, can 4G and 5G networks evolve to move their base station functions to a 6G cloud?
So the answer to that is yes. The transition to cloud is actually independent of the waveform. What would have to happen is those base stations would have to reduce the reliability on a local scheduler and a local channel detection and estimation, and just send that information through backhaul to the data center, and all of those functions could be performed there. Now, it's commercially challenging because those companies have sold those base stations with that content in it, and to turn it off would obviously reduce the value. But it's not only technically possible, it's actually quite beneficial to the operators to do that.
Excellent. Thanks ever so much, Ray. I appreciate that. Now, I know that you're sort of up against time, and so are we. So let me say thank you now, and hand over to Andreas Rosler from Roden Schwartz.
Thank you, Alex, and congratulations.
Thanks.
All right. I want to thank Ray for laying the foundation. I want to expand a little bit on that. I have to admit I'm not as efficient as Ray was and put everything on one slide. So I have a few more. But basically, I'm gonna talk a little bit about the 6G research that we already explored a little bit. And here is the scenarios, the 10 scenarios that Roden Schwartz thinks are covered by current research around the globe. Ray mentioned here the United States. I think many of you in the audience are aware of the Next G Alliance that's pushing the 6G roadmap and technology for North America. There are similar initiatives in Europe with these research projects, and all of them, as Ray already mentioned, have a component of AI and ML in it. We listed here as one technology component, but to tell the truth, we basically can see that all of the emerging technology components that are currently being researched are using artificial intelligence and machine learning to a certain degree. Ray mentioned the waveforms, the channel estimation, equalization. That's definitely a massive piece and will impact, of course, test and measurement as well. So they're very great ideas, but the question is really, what role will machine learning play in 6G? Is it just a hype? Is it a steam engine, or is it a bullet train? And if we ask ourselves that question in relation to the Hitchhiker's Guide to the Galaxy, a global question of the universe, the answer may not just be like 42. Like Ray mentioned, we already have today with 5G in release 18, which is about to start exploring the AI and ML framework for wireless, for the air interface, and for the next generation radio access network. We can compare that from our perspective to the nuclear fusion process that takes place in our sun today and is so eminent and important to life. So you see 5G machine learning fusing there to what eventually we will call 6G, creating some innovation. And I have to think about the byproduct right now, because in the fusion process, that's a neutron, of course. But we need to think as an industry what that might be. So we all know that machine learning is based on neural networks, and I don't want to give you an introduction to that. I just want to talk about, from a test and measurement perspective, you may all be familiar that we're characterizing transmitters today with a signal quality measurement that's called error vector magnitude, which is the top KPI that we measure according to methodologies and procedures that are defined in the standard, based on waveforms, on test models on the base station side, on fixed reference channels on the device side, and such. And as test and measurement company, usually us and our competitors are evaluated by the industry measuring error vector magnitude over a power sweep. And Roden Schwartz and our friends in the world did a great job of providing technical explanations, webinars and seminars around this, and what's the best procedure. So what you could think now, if you thinking about machine learning, you could now take certain input parameters like frequency, power level. We talked about the waveforms. So typically waveforms have different crest factors, depending on if it is a single carrier or a multi-carrier scheme, then the bandwidth, the subcarrier spacing. So all these great parameters on the physical layer. And we can train a neural network now to find the best reference level, the best attenuation setting, and eventually internally in the equipment, I'm talking about a spectrum analyzer here, also do fine-tune parameters to optimize this measurement functionality. However, doing machine learning for the sake of machine learning makes no sense, right? So what you see here, 2 examples of our spectrum analyzers on the left-hand side, signal generator on the right-hand side from Roden Schwartz. Those functionality is already implemented since a very long time in the standards to assist customers to do that. So what I'm trying to say is, like, you shouldn't look at machine learning just because it's cool and there's a buzzword to do it. You should really identify the use cases where they bring a benefit to our industry. And I think we're starting with that with release 18, and we'll explore that as an industry, as a community, over the next set of releases, and that ultimately then ends in a release that covers also a 6G standard. So as you see here, release 18, the first steps are being taken. The official timeline shows that there's an ASN1 sort of syntax freeze by March 2024, which implies that the core specification is ready by December 2023. And that's about 18 months from now. So quite some time, and I'm sure that Alex and the team will cover items in that direction in a future event. Usually we have a poker game there between the industry players that discuss what should be in there. So it's quite a eye chart from that perspective. For this particular discussion in December, there was some narrowing it down. And for this particular discussion today, we want to look at this particular study item here. And you see that 3GPP will focus on 3 use cases: CSI feedback enhancement, beam management, and precision accuracy enhancement. I would like to spend a few more minutes on discussing why CSI feedback enhancement is, for instance, a very relevant use case. Well, why is that a use case, you can ask? What you see basically here is like a quick summary of a very complex topic on one slide that discusses how we derive the channel state information today in 5G, and focusing on the downlink in that particular case. So we have these CSIRS, the channel state information reference signals. Their configuration depends on the hardware capabilities of the different vendors. It's a network feature from that sense. The standard supports up to 32 antenna ports. We all know that an antenna port is a logical unit, and they are typically mapped to multiple antenna elements, and dual polarized and such. So if we look at all these different items, and what you see here very basically is the configuration that could be applied in order to enable that based on a vendor specific thing. If we would now estimate the channel, the full channel, we would rather end up with a tremendous amount of feedback bits, which is summarized in this table here. And for those of you who are very much interested in all the details, I'm pointing out this paper that's just being published by Samsung Research here in February 2022. So you see with the release 15 functionality, we have here about 351 bits, which is quite a significant overhead that we would have to transmit if we want to do that. So what is 3GPP doing? Of course, they invented a lot of procedures and functionality that's embedded in the standard that makes it tremendously complex to wrap your head around this as one individual, to reduce how we producing this feedback in order to reduce this overhead that you can see here. Initially, academia started to look into that particular topic that you can see here very simplistically shown, where we have on the left-hand side a certain number of transmit antennas and receive antennas, a certain number of paths with some reflections in a 4x4 MIMO setup that ultimately leads into the assumption there are 24 path, 16 antenna pairs. We have an imaginary path. We code that by 32 bits. So the estimate each and the entire path, which ends up in this tremendous amount of bits that have to be transmitted. So what the academia looked into is basically how we can compress this feedback. And there's where they go into machine learning and using an autoencoder, which is a specific type of neural network that was originally invented and designed to do compression to remove redundancy from data. And the goal is basically to do that and minimize the error. And the academia community came together here and used different architectures for compression, for quantization. And as you can see, the winning team, there were about 900 teams, and they're all, the entire thing is analyzed in this particular paper that I list down here, which I encourage you to read, was able to reduce this feedback by a factor of 86. So quite significant here. And now that 3GPP is adopting this concept or researching that from a 5G perspective, of course, we could see a lot more momentum and movement here. So what comes after that? I think Ray touched on that already, moving channel estimation equalization back to the cloud. I think that's state of the art. You can find a lot of papers right now where machine learning models have been developed to take over this functionality and to prove that there's an additional benefit. We see now that the next step could be to combine these functionality of detection, estimation, equalization, and demapping into individual models, and ultimately move to the phase where the physical layer designs part of itself using an autoencoder approach, not to compress the data right now, but to learn the link end to end, not just including the RAN and the interface, but also the type of application that should be delivered over that existing link. And always it's different to put a timeline behind that, but I think it will be somewhat a sequential approach to gain more experience with this, with a phase 1, a phase 2, and a phase 3. And you see here some question marks already because there are some associated challenges with that. The phase 1 is most likely the most easiest one. As you can see, there's quite some activity in academia already since more than 2 years. And what I like about this is if you're looking at these papers from the left to the right, then you can see the October paper actually referencing the April paper from a Chinese university, and taking up their approach, their design approach, their specifically design neural network, and claim to achieve an improvement in performance there. So you can see that we build up now on these successes, and using, for instance, something like machine learning to learn memory effects that are introduced by the RF front end and linearize it based on that. And of course, no machine learning without data. And we're exploring that as well. So you see again our generators and analyzers on the side, device under test. Typically, all these papers usually are based on a power amplifier right now. They will move to the entire front end, including the internet subsystem. And you basically can now collect data, create data because of the flexibility in the equipment. We can do something that's we called an iterative digital predistortion, where we're doing it over and over again on the same waveform, and ultimately correct for any impact that the test equipment had, and purely figuring out what the hardware is capable of for that particular waveform. But then we have to keep the real-time aspect of the signal in context here, and we can train the network here on multiple different signal configurations, and so achieve a better result than or close enough result to what the actual hardware will be capable of. So this is something that we explore with our partners and customers, of course. The next step, I mentioned it, is the mapping, is the combination of different signal processing blocks. I think Nokia Bell Labs did a great job here, educating our community on what's possible. You see here one of those talks coming back from the November from the ITU AI/ML challenge, 5G for good. And you can basically see here, if you're not familiar with it, Burr curve over SNR, and where we see that the baseline, the standard LLM-SE receiver architectures towards perfect channel knowledge. And right in between there, we see neural receiver approach from today's baseline performance, almost accomplishing a 3 dB improvement due to a data-aided channel estimation and equalization and demapping trained neural network. So in 3 dB, it means double, right? So that's a significant improvement for those who will ask questions why we're really looking into this and using machine learning potentially on the physical layer, especially if it comes to the design of the 6G physical layer. Our question to that is, can we support this research? Because right now it's all synthetic data, right? Designed or generated in simulation environment. And I think yes, we have a share in this. It's a little bit of a complicated eye chart, but basically what I'm trying to tell you is like, okay, you have the fading profiles implemented, but the great stuff is you can also do a customized fading based on channel sounding data that you have. We can imply analog and digital impairments into the data sets, which helps us to mimic real transceiver behavior. And that, of course, is some advantages if it comes to pure non-data driven environment in a simulation, when you're going to hardware in the loop experiments to check your implementation once you're taking it from the GPUs, where it's always looking great, and have implemented that into a specific ASIC or FPGA design. And last but not least, and this is my last slide, is the autoencoder transition. There's quite some research going on in that. It also shows that there might be additional performance gains in terms of efficiency. For instance, we can reduce or get rid of the transmission of so-called pilot signals, which are adding redundancy into the signal. But the question is really how practical a solution like that will be in real life. As we all know, we have network operator who operating the network. We have the infrastructure community. We have the modem vendors. We have the OEMs designing devices. And the question is really how scalable is that? If I control both points into the end-to-end link, yes, autoencoder and learning the end-to-end communication link via an autoencoder seems to be plausible, feasible. But the question is like what our community has to do to enable that with a multi-vendor environment. And if communities or organizations like ORAN will take this on and support this even further, what 3GPP is doing, and how is that being handled. So this is an interesting question from our perspective. We're looking forward to support the industry in solving these challenges, addressing these problems. And with that, I would like to turn it back to Alex. Maybe we have even questions that Ray or I can further answer from the audience. Thank you so much. Back to you, Alex.
Thanks ever so much, Andreas. So there's one thing that leaps to mind as you mentioned this, and as you say, this is a situation where we're looking at both AI and cloud working together. It seems as though that's going to make a whole new dimension of challenge in terms of the coordination or orchestration, particularly if we're thinking about crossing between sort of different network owners or different domains. So we haven't really covered a lot about that, but did you have any thoughts as to how that gets tackled, or what the process might be to do that?
Yeah, that's the exciting question. I think that the industry is trying to answer within these different industry alliances right now, right? I mentioned Next G Alliance here for North America, where things like that are extensively discussed among the community. From our perspective, for instance, we believe that eventually we have to come up with combined KPIs, right? That cover all areas, that cover link performance from an air interface point of view, but also typically performances that are measured in IP-based networks like latency and things like that. And I think it's our task to come up with a good set of parameters that helps us to analyze and describe the behavior of the network, not just looking at the individual components, rather, the remote radio heads, the DUs, the RUs and so forth, but the overall perspective. And I think that's something that will happen over the next couple of months. It needs to be agreed, right? How this is being handled. But that's, I think, the best answer that I have for that question right now.
No, that's very fair. And there's, I guess, something that builds from that maybe, and that's the idea of taking one of Ray's suggestions about the idea of waveforms being tailored to particular applications and services, I wonder if actually sort of looking at the performance from the application or the service perspective rather than the network perspective is something that you've also got your sights set on, or whether that's actually something left, better left, I guess, to the application providers themselves.
Yeah, it's a very good question. I mean, I think we will see we need to have some synergies beside that, not just like that the application will drive what at the end of the day should happen on the air interface, but it needs to be in a controlled manner, I would assume, right? Because if everybody's just doing whatever they want, then we will create even more interference and make it more complicated. So I don't have really good thoughts on that yet, because we are not the cloud provider nor an application developer, right? We're just trying to make sure that every player can verify its approach using test solutions, and maybe even we have to look further into that and talk to the app development community even further than we have done so in the past, right? So that might be an outcome of this early engagements and discussions provided by the forum that you offer right now here, but also in the other industry alliances that are being established to explore this scenarios.
Fantastic, thanks, Andreas. If that is a useful outcome from something like this, then I think we're hopefully doing what we need to do. Now, I realise that for our audience, we're getting close to time. So let me just say that for anyone attending, you will be able to access the video recordings for this keynote session and those of the other 15 sessions at the symposium next week on the 6GSymposium website. There's an amazing quantity of insight to be gleaned just already from day one, so I strongly encourage it. Tomorrow in day 2, we'll be focusing a lot more on the commercial objects of getting towards 6G, and then on Wednesday we'll dive more deeply into some of the technical aspects, including questions of waveform, network architecture, and so on. So if you can, join us. If you can't, do please feel free to take advantage of the videos. It just remains for me to thank Andreas, Ray, and you, the audience, and I hope you can join us tomorrow. Thank you very much.